everybody, welcome to Nikon to another video podcast. I hope you are doing really fine. Today we're gonna be talking about physics of an aircraft during climb and of course the two main performance factors, rate of climb and the climb gradient. So in general and more realistic situation that the flight path of the aircraft is a curve, as we see here with the blue line in the sketch. During its climb we have for the tangent axis from the second law of Newton, that the aircraft also in the general situation that is accelerating, that thrust minus drag minus the tangential component of weight equals to mass acceleration for the perpendicular axis, that one. We have that since the aircraft is in a curved flight path, we have centripetal acceleration, so that would be lift minus that component of the weight equals mass and centripetal acceleration. But if the aircraft's motion is linear in a constant angle of climb, then the flight path would be that one. So in this case the situation is simplified, so we have that the aircraft still is accelerating in this axis, but in this axis the aircraft is in equilibrium. So in that case, lift minus perpendicular component of weight equals to 0, which means that lift equals this. In any case, from the first equation multiplied by the airspeed, we have that so that factor is the vertical component of the airspeed, as we can see here, which in turn is the rate of climb of the aircraft. And the acceleration is a change of speed over time. So if we change the differential here with the altitude, this factor is the change of altitude on time, which is exactly the same with the vertical speed. So also this factor is the rate of climb. And if we solve the equation for rate of climb from here, we finally have that and in that fraction, if we divide the numerator and the denominator with the weight, we are going to have So let me rewrite the final result that we have here, which is that the rate of climb in the general situation that we have an aircraft which accelerates during its climb is going to be this. And what does this mean? What is all that about? The numerator, as we can see, is the classic rate of climb when the aircraft is not accelerating, thus when it's climbing with constant airspeed. So let's call it rate of climb with zero acceleration. In the denominator of the fraction, the second factor, this one, is called acceleration factor. And why? Because exists only if the aircraft speed changes with height, as we can see here. So if the aircraft accelerates or decelerates during climb. Therefore, with that in mind, we can rewrite the equation in that form, where acceleration factor is that term. Of course, we can see that if the aircraft speed is constant when it's climbing, then this term, the change of speed over altitude over height, will be zero. So, in that case, the acceleration factor also will be zero. In that case, that the aircraft is climbing with constant airspeed, the rate of climb is going to be equal to the rate of climb with zero acceleration, which is thrust meon drag minus drag multiplied by the airspeed divided by the weight. And that is this is the available power, this is the required power, which is taken of the aircraft by drag, and all divided by the weight. And finally, this is the excess power that the aircraft has divided by the weight. All this just in case, only in case that the acceleration factor is zero, which means that the aircraft climbs with a constant airspeed. And of course we can sketch the situation here. Let's put the vertical axis the power and the horizontal the airspeed. Supposing that we deal with a jet aircraft, so the available power will be that, and the required power will be that kind. So we see that the difference of the two, the available power and the power required, will be, in any case, for different airspeeds, the distance between two curves. So if we sketch that difference, of course will be the rate of climb, and the curve will have the same form. So we can see in that case that as the aircraft speed increases, we have an airspeed for which we have maximum rate of climb, and we call that airspeed Vy. In order to determine the acceleration factor in the case that the aircraft accelerates during climb, the speed altitude profile of the aircraft must be known. In general, two profiles are of special interest. The first is a climb with constant indicated airspeed until the crossover altitude, and the second is the climb with a constant Mach number after crossover altitude. So in any case, during climb in troposphere, the true airspeed does not remain constant, so in reality an acceleration factor exists. Another performance factor during climb is climb gradient. Climb gradient is simply the tangent of angle of climb expressed in the percentage form. So, from the climb formulas with no acceleration, with constant airspeed, supposing this time, we are going to have in the parallel axis there is no acceleration, as we just said, so it will be thrust minus drag minus that component of weight which is this. So if we are going to solve for this factor, we have this relationship, this formula. Let's call it 1. In the other axis, where also the aircraft is in equilibrium, we have that the lift is equal to this component of weight. So we have that lift equals to the perpendicular component of weight. Let's rewrite it in that form and let's call it 2. If we divide the expressions 1 by 2, we have that so sinus divided by the cosinus, it's the tangent of the angle of climb and we have this relationship. But taking into account that the angle of climb is not extreme, is general less than 20 degrees, so we have some assumptions that when the angle of climb is the general angle is less than 20 degrees, we can assume that the sinus is almost equal to the tangent of the angle and the cosinus is almost equal to 1. So from that assumption, from the second assumption, we have that if the cosinus is almost equal to 1, so from the second relationship we have that the lift is almost equal to weight, so we can rewrite the final form that the tangent of the angle of climb is thrust minus drag divided by the weight. But from the definition of climb gradient is simply the tangent of the angle of climb, but expressed in a percentage form. So we have that the climb gradient is the tangent of the angle of climb expressed in a percentage form, which means and that's the final formula for the climb gradient. Always in a climb with constant airspeed. And from the last expression we can see that thrust minus drag is the excess thrust, since thrust is the thrust available and drag is in essence thrust required. So we can sketch the vertical axis we put thrust and drag forces, on the horizontal axis we put the airspeed, and assuming a jet aircraft again, which has a thrust almost near constant with speed, and drag, classical drag curve, we can see that this difference between, let me rewrite it, between thrust and drag is for every different speed the difference between two curves. So we can see that there is one speed where that difference is maximum. If we make a new graph for the climb gradient with airspeed, it will have the same form, and of course we can see the same speed for which we have the maximum climb gradient, which corresponds to the speed that we call it Vx. And this is the speed for minimum drag, which is the same for jet aircraft. Finally, of course, the difference between the thrust and the drag, it's the excess thrust that the airplane has. So we could rewrite this expression as excess thrust divided by its weight by 100%. Finally, we'll examine the relationship between rate of climb and climb gradient. Rate of climb is not independent from climb gradient, since if we take a look at the speed vector, we can see that from here sinus of the angle of climb is the vertical speed divided by the airspeed. So this is the rate of climb, and since the angle of climb is less than 20 degrees, sinus it's almost is approximately equal to the tangent of the angle of climb. So the rate of climb is equal to the true airspeed multiplied by the tangent of the angle of climb. But here the rate of climb is in knots. If we transform knots to feet per minute, which is approximately 1 knot, approximately to 100 feet per minute, then the rate of climb will be the true airspeed multiplied by tans of theta percentage, which is, as we know, the climb gradient. So rate of climb is proportional to true airspeed and climb gradient. With that in mind, we can make a final diagram having the two axes, the rate of climb. Let me rewrite this. And of course the true airspeed. We have already viewed that diagram. I'll make it again. It has that form. So we can see that the rate of climb is a function of true airspeed and the climb gradient, but climb gradient is also a function of excess thrust, which in turn is a function of speed. From the last graph is also clear that the tangent from 0 point can give the maximum climb gradient. So every other climb gradient would be less for greater airspeeds than this or for smaller airspeeds than this. So in that case we have, of course, the maximum rate of climb, which corresponds to Vy, and the maximum climb gradient, which corresponds to Vx. Of course, this is true because from that relationship, climb gradient is rate of climb divided by true airspeed. So, the climb gradient mentioned in any case of this video is climb air gradient. In order to find the ground climb gradient, thus the climb gradient with reference to the ground, we have to know the wind conditions. So in that case, the ground climb gradient will be the air climb gradient multiplied by this factor, which is called wind factor. So that's the way, if we know air climb gradient, to find the ground climb gradient, or vice versa. So I think that's a lot of information regarding the climb. If you have any questions or something to add, please write a comment below. Thank you again very much for watching. Have a fantastic day. I'll see you next time. Bye bye.